Hello class, welcome to this video on the AP Statistics Chapter 9 test. So we're going to look at one of the versions of the test. So let's take a look at the first question. So it says television networks rely heavily on ratings of TV shows when deciding whether to renew a show for another season. Suppose a network has decided that Miniature Golf with the Stars will only be renewed if it can be established that more than 15% of US adults watch the show. So we got more than 15%. A polling company asks a random sample of 200 US adults, we got a random sample, if they watch Miniature Golf with the Stars. In this random sample, 32 confirmed they watched the show. Explain why there's some evidence for the alternative hypothesis. And part B, is this result convincing evidence that the true proportion of all US adults watch the show? So we're dealing with proportion, we're dealing with a single proportion, so one sample. And when we're dealing with proportions, we could use the Z test. Okay, so let's do that first. Let's state the type of test we're going to do. So we'll state it, and we're put it in our plan. So let's state our hypotheses. So H, O, and HA. So our null hypothesis is that the proportion P of all US adults that watch the show Miniature Golf with the Stars, we're going to say that it's 15%, 0.15. But then for it to be renewed, we need it to be greater than 0.15. Okay, so then we have to define where P is. Okay, so where P is equal to the true proportion of all US adults who watch the show Miniature Golf with the Stars. All right. Okay, so then we're going to do the plan. Okay, so before we do the plan, let's just do the part A. So now we can answer part A. The alternative is that the true proportion of all US adults who watch the show is greater than 15%. And so why is there some evidence for that? Well, in our random sample, we got P hat of 32 out of 200, which is equal to 16%, right? So it's equal to 0.16, which is greater than 0.15. So there is some evidence for HA. All right. Okay, so now let's go to part B. Let's go switch back to that. So our plan is to do a one sample Z test for P. All right, so that's our plan. So now we have our conditions that we have to meet. So we have a random condition, so which we do have, right? It says that a random sample of 200 US adults was selected. All right, so that's good. And then we have to meet our 10% condition. So we're going to say that 200 is less than 10% of all US adults. All right, and then we're going to do the large counts condition. So we're going to say we're going to need to calculate, so we need to do 200 times 0.15, which if you did that, you get 30. And remember that this should be greater than or equal to 10. And then we'd have to do 200 times 1 minus 0.15, which is 170, which is greater than or equal to 10. So that meets both criteria. All right, so now we can do, and we're going to calculate our Z. All right, so remember, a statistic minus parameter. So yeah, statistic minus parameter. Let me just write it off to the side here. So this is what they give you in your formula sheet, right? They give you that the standardized thing is the statistic minus parameter divided by the standard error of statistic. Now, if you go to the formula sheet, they'll give you a couple of things. They'll give you the standard error for p hat, and they'll also give you your standard deviation for p hat. Okay, so they'll give you the standard deviation for p hat is square root of p times 1 minus p divided by n, and then they'll give you the standard error is p hat 1 minus p hat divided by n. Okay, so they'll give you those two things. Now, which one are we going to use? Well, normally we would use the standard error, right, according to the formula. However, there's a disclaimer. If you know what the standard deviation is, then you would use that instead, because the standard deviation, remember that the standard error is supposed to be approximation of the standard deviation. So if you know the standard deviation, then you should use it. So in this case, we're going to use the standard deviation because we know what it is, because we know what p is, right? P is the hypothesized value, right? Which is 0.15. So we're going to plug that in. Assuming that p is 0.15, then we know the standard deviation, we can plug it in. And the statistic is p hat, and the parameter is p. And so here we can get the z-score as follows. We got p hat minus p divided by square root p times 1 minus p divided by n. All right, so there you go. So now we know where our p hat is because we calculated earlier, it's 0.16. And our p is 0.15. That's our, so we usually call this p naught here because, because that's from the hypothesis. So sometimes you'll see that labeled as p naught. All right, so over square root, and then we got 0.15 times 1 minus 0.15 divided by, we had a sample of 200 US adults. All right, we can calculate, see what that is. Okay, so then if you calculate that, you get about 0.40, okay, to 2 decimal places. You get about 0.396 approximately, which is about 0.40. Let's double check that actually. So this is 0.01 divided by square root, 0.15 times 0.85 divided by 200. Okay, so yeah, you get about 0.40. So there's our z-score. So we're going to label that on here. We got, this is about, sorry, it's about here. Now, if you look at the test, it's a right-tailed test. So we're going to shade to the right here. You can see our p-value is pretty large for this example. So we can calculate the p-value next. So let's go ahead and do that. So the p-value, so we're going to use the normal CDF function, but we can also use the one test for z, the one samp z test, which we'll show you on the calculator in just a second. But if you use this function, then you would use lower is 0.40, the upper is infinity or 1000. You can use 1000 if you want. The mean is 0 and the standard deviation is 1. And we'll figure out what that is. All right, here we go. So we're going to hit stat, or we're going to go to second vars, and we're going to go to normal CDF, and then we're going to go hit 0.40, and then 1000. You got 0 and 1, so that's good. So we go to 1. All right, so we get 0.3446. We'll round to. Now, while we're here, let's try the test. So we're going to hit stat, and we're going to go to tests, and we're going to do the one prop z test. Okay, so we have one sample proportion z test, and so this one was 0.15 for the p naught. It was, I think it was 200 for the population, the sample size rather. Or no, I'm sorry, it was 200 here for the sample size, and then it was 32 here for the amount that said yes to the question, and it was a right-tailed test, and so we can calculate, and look at that, we get 0.3446, which is 0.346, which is very similar to what we got using the normal CDF. All right, so now that I showed you both ways. So we get the p-value is about 0.345 or 0.346, depending on which one you did. So we'll just say about 0.345 for us. And so now we know that we can conclude here. All right, so we can do the conclude stage. And okay, so then we can say since the p-value of 0.345 is greater than alpha, and we need to actually specify our alpha, and we would normally do that in the state stage. So state our alpha. So for alpha equals 0.05, we assumed, because they didn't actually give an alpha. So we would normally put that in the state stage, but you have to make sure you include it there. All right. So is greater than the 0.05. Since it's greater than that, that means we fail to reject. So we fail to reject HO, which means that we don't have convincing evidence. Okay, so there is say there is not convincing evidence that the true proportion of all, and in this case, remember it was US adults, is what? So is the HA, which is greater than 0.15. All right, so there you go. So that takes care of that. So now we're going to interpret the p-value. So then we got the p-value 0.345. So let's go ahead and interpret that. Remember that the p-value, the definition of the p-value, it assumes that the HO, it assumes that the null hypothesis is true. So assuming that the null hypothesis is true, there is a 0.345 probability that we would have enough evidence to support the alternative hypothesis. Okay, so something like that, of that sort. Or I guess we should say rather, we would probably say it this way: the assuming that the null hypothesis is true, there's a 0.345 probability of. So we wouldn't say the alternative is true, convincing evidence. That would be for like the power and things like that. It would be a 0.345 probability that we would get a sample result as strong as, in this case, 0.16 or higher, right, or larger, by chance, basically. Okay, so that's what we're going to use here. Okay, so we're going to say assuming HO is true, meaning P is 0.15, right? There is a 0.345 probability, I think that's what it was, right? 345, yeah. Probability of getting a sample proportion, P hat, of 0.16, because that's what we got, it was 0.16, right? That was our sample proportion, or larger or greater. Now we would say greater because that was the alternative hypothesis, okay? So 0.16 or greater, purely by chance. All right, so there you go. So now we're going to describe a type 1 and type 2 error in the setting and give a possible consequence. Normally I would give you a whole bunch of space here. I'm surprised that it doesn't look like there's a lot of space here. So we might just do here and then continue the, the possible consequence in the next one, if we run out of room, that is, okay? Okay, so we'll start with type 1, and then here, if we run out of room, then we'll just continue below D. All right, so type 1. Remember, type 1 error is when you reject a null hypothesis, which means that you support the alternative hypothesis when you're not supposed to. Okay, so in this case, we're going to find convincing evidence that the true proportion is greater than 0.15, right? When we're not supposed to, when it really equals 0.15, right? So that's how the type 1 is going to look like. So the network finds convincing evidence that the true proportion of US adults who watch miniature golf with the stars is greater than 0.15 when it actually equals 0.12 or 0.15, sorry. When it actually All right, so there's our type 1 error. And we'll go ahead and continue this here. So we'll say D continued. And we'll do the consequence. So what's the natural consequence or possible consequence of that? So we'll say the consequence. So in this case, well, in that case, then the show will be renewed because they found convincing evidence, right? So the show will be renewed. However, then we notice that there's not interest in the show when we renewed it, right? So the show is renewed but interest does not support it. All right, so then let's do the type 2. Okay, so now type 2 is the network doesn't find convincing evidence that the true proportion of US adults who watch, we can put ... here because we've already, that the true proportion of US adults who ... is greater than 0.12 or 0.15 when it really is greater than 0.15. So they failed to find that evidence to support that, but they should have, right? Because it really is greater than 0.15. So then we can write a consequence for that, which is the show will not renew even though there is a market for it. All right. Okay, so now let's look at power. Sorry, I almost forgot the power, part E. So the power of the task to detect that P is equal to 0.16 based on a random sample of 200 US adults is 0.11. So assuming that the p hat that we got is the actual value of p, so we're assuming that the 0.16 that we got is going to be the value of p. So that if that's true, then if that's a true value, then based on a random sample of 200 US adults, the power of the test to detect that is 0.11. So interpret this value. So again, the power, what it does, it assumes that the value here is true. So given that this value is true, the 0.16 value, then the probability of finding convincing evidence for the alternative hypothesis is 0.11. Okay? That's basically what we're going to say. All right, so let's go ahead and do that. So again, we're assuming that the true proportion is that. So we're assuming that that value is true, okay? So if the true proportion of all US adults who ... because we've written it many times, who watch the show, right? Is P is equal to 0.16, there is a 0.11 probability that the network will find convincing evidence for HAP is greater than 0.15. Okay, so it's actually a very small probability that we'll find that evidence, which is telling us that the power of the test is low, which means that the probability of making a type 2 error is high. So if they asked you for the probability of type 2 error, this is not what they're asking for, but if they asked for it, the probability of type 2 error is 1 minus the power, right? So it's 1 minus 0.11 or 0.89. So the probability of type 1 error is, probably 0.05 here. Yeah, it was 0.05. And the probability of type 2 error is 0.89. So the probability that we fail to, fail to find convincing evidence for the HA when we really should have is 0.89, which is pretty high. So it's something to keep in mind. And this is, of course, assuming that 0.16 is the true value. That's what this is assuming here, okay? All right, so here we go. So let's take a look at number 2. So a study by the National Athletic Trainers Association surveyed random samples of 1,679 high school freshmen and 1,366 high school seniors in Illinois. Results showed that 34 of the freshmen and 24 of the seniors had used anabolic steroids. Steroids, which are dangerous, are sometimes used in an attempt to improve athletic performance. Researchers want to know if there's a difference in the proportion of all Illinois high school freshmen and seniors who have used anabolic steroids. Okay, between high school freshmen and seniors. Explain why there is some evidence for the alternative hypothesis. They're saying that there is a difference, which means that it's not equal to, like basically when you subtract the two proportions, it's not equal to 0, right? So this is a 2 sample. Notice that, right? We have the freshman group and we have the senior group. So we have we have N1 and N2, right? So where N1 is the sample size for the freshmen and so on. So we're going to first we're going to state our hypothesis, because it says what can you conclude at the 10% significance level. So we're going to do that first. Okay, so we're going to say, all right, so H0, we got P1 minus P2 is equal to 0, meaning that there is no difference between the freshmen and the seniors. And here we think that there is a difference, so that's going to be the alternative, right? So it does not equal to 0. In other words, there is a difference between the two groups. Okay, so now we have to define what P1 and P2 are. Okay, so where P1 is the true proportion of all freshmen all high school freshmen in Illinois that use anabolic steroids. And P2 is the true proportion of all seniors in Illinois that use anabolic steroids. Okay, so we have that. So now let's see, is there enough evidence? Let's calculate that. Let's do the P hat 1 and see. It says there's 34 freshmen out of 1679. So we got 34 out of 1679. And then we would have to calculate P hat 2, of course. So for the sophomore or the seniors, we got 24 out of 1366. Of course, we're going to have to determine what these are as a decimal, and then we can subtract them. So let's see what they are. Okay, so we got 0.0203. Okay, got 0.0176. All right, so we'll go ahead and subtract those and see. So we got P hat 1 minus P hat 2 is 0.0203 minus 0.0176. Okay. Go ahead and subtract that, of course. So 0027. Okay. All right, so there you go. So there's some evidence because it's not equal to 0, the difference, okay? Although it's very close to 0, but still there's a little bit of evidence. And so we'll need to see if it's significant or not. We might think that it's not, but we'll have to test it just to be sure. Okay, so we'll go ahead and test it. So we got to do our plan of action here. So we're doing a 2-sample z-test for the difference in proportions, P1 minus P2. All right, so then we'll have to check our conditions, of course, right? So random condition. So let's take a look here. It says they surveyed random samples of freshmen and high school seniors in Illinois. Okay, so it looks like there's 2 randomly selected samples of 1,679 freshmen and 1,366 seniors in Illinois. All right, and so that check on that, and we got to do the 10%. So we're going to say 1,679 is less than, we're assuming that that's less than 10% of all freshmen in Illinois, in the entire state of Illinois, which is reasonable, right? And we're assuming, that 1,366 is less than 10% of all seniors in Illinois. We're not talking about a specific school, we're talking about the state, right? All right, so that's good. And then we have the large counts. All right, so we got 1,679 times, then we got to do the, here we have to combine them into one p hat, right? So we have to combine these. So let's calculate that first. So we need to calculate the combined or collected p hat. So we need to do the pooled p hat or the combined p hat. All right, which means you got to add up the, well, I'll write down the formula. So this is you add them up. on the numerator and then add the total on the denominator. All right, so we have 34 freshmen that said yes to taking steroids, and then 24 seniors out of 1,679 plus 1,366. Okay, and let's see what that is. We'll do it on the calculator. Okay, 0.019. So we don't have to round it. That's good enough. All right, so there's our collected p-hat. And then so now we can test them for all of this. So we could do n1 times p-hat. So 1,679 of the freshmen times that value, okay, the p-hat c value. So let me write it out here just so that there's no confusion. So there's that times the 0.019, and then we need to do this times 1 minus. And then we'll do the n2 p-hat c. n2 1 minus p-hat c. So you have to make sure you deliberately show all of them. Okay. All right, so let's go ahead and test these out. 1679 times 0.019. So 31.901 greater than or equal to 10. So let's check for that. We could do 1 minus that. So 1647.099 greater than or equal to 10. All right. So 25.954 greater than or equal to 10. All right, so we got 1340.046 greater than or equal to 10. All right, so obviously it passes all of them, so we're good. We can go ahead and move on to the do stage. And so let's go ahead and calculate the z-score and all that. So remember, the the standardized score, the standardized test statistic is equal to the statistic minus parameter over the standard error of the statistic, right? And so this test statistic is z, right? As opposed to the t or whatever. And then the statistic is, well, we're doing p-hat1 minus p-hat2, right? And then the parameter is p1 minus p2. But we know that this is equal to 0, so we're going to just put 0 there because of the null hypothesis, right? And then now the standard error, right? The standard error, we have the standard error and then we have the standard deviation. So let me do that. The standard error of p-hat1 minus p-hat2 is square root of s squared 1 over n1 plus s squared 2 over, oh wait, I think that's the, sorry, that's the wrong one. That's for the one, that's the other one for, that's for means. I was thinking about that. So it's going to be, okay, so here I figured it'd just be better to show you the formula sheet. So this is the formula sheet, and then we're looking for two populations, right? All right. Okay, so we got two populations, p-hat1 minus p-hat2. And so you got this one for sigma hat, p-hat1 minus p-hat2, which is this, p1, 1 minus p1, p2, 1 minus p2 over n1, n2, all that stuff, right? Now, we could use that, but remember, we found p-hat c, right? So since we found p-hat c, we're going to use that instead, okay? Because we actually are using p hat c in order to combine the p's. Okay, so if that makes any sense. So since we're combining them, we're going to use this one. So this one's one where you know you're using p hat c, so you might as well use this formula, right? This is going to be the one. So p hat c, so we're using this guy. Okay, so yeah, so I just wanted to show you that. Hopefully that kind of clears that up. So since we're going to use p hat c, so then that means we're going to be using this one right here, the one with p hat c. Rather than using P1 and P2, we're using that, okay? All right, and again, just remember, we're using p hat c, so we might as well use this formula. It just makes sense, right? So it's an easy way to remember. Okay, so let's use that formula. So I'm going to rewrite it. Minus 0 divided by the square root p hat c, 1 minus p hat c times 1 over n1 plus 1 over n2. Okay, so we got p hat 1 minus p hat 2, so 0.75 minus 0.58 minus 0 over the square root of, what did we get for p hat c? We got 0.019 times 1 minus that times 1 over 1679 plus 1 over 1366. All right, and of course you can calculate this, but you can also use the p hat, the two sample two proportion z test, right? So you can use that and it'll help you to get the value. So we'll do that. We're actually going to use that two proportion test so that we can just figure out what that is. But I'm showing my work for the z. And then we'll actually use that to get a p-value as well. Even though you could use the normal CDF, right? You could use normal CDF. And I'll do both ways. So if I do the two prop z test, so two prop z test, and so we have to report our z, and then we have to report our p-value, okay? So we're gonna do that. Okay, so let's do a two prop z test. So we're gonna go to stat, we're gonna go to test, we're gonna do two prop, and we got x1, so that's, it was 34 freshmen out of 1679, and we got 24 seniors out of 1366, and we had a two-tailed test. We're going to go to calculate. Okay, so we get our p-value, so notice that you get the p-hat. This p-hat is the p-hat collected, the collected p-hat, which is 0.019. That's what we got, remember? And then if we go down, and we got our z-score, 0.538. So we're going to round that to 0.54. And there's our p-value up here, so 0.59 for our p-value. Okay, so there you go, and that's all the other stuff. All right, so that verifies it. Okay, so we got 0.54 and then 0.59 for the p-value. Okay, so then we get z is 0.54, and then we get p-value is, so let me just report z is 0.54, p-value 0.59. All right, so we got, and I like to label the stuff. I like to label all the things. So z got 0.54, and it was a two-tailed test. So remember that it's on the right side and on the left side. So we have to do the negative version as well. And that explains why it's such a large value for the p-value. And we can double check this with the normal CDF. So we're going to do the normal CDF to see if that's the case. All right, so because it's a two-tailed test, we have negative 0.54 and positive 0.54, and we were basically doing two areas. So we're going to do 2 times the normal CDF function. The lower limit, we're going to use negative infinity or negative 1,000. Upper We're going to use negative 0.54. Mean is 0. Standard deviation is 1. So I'm curious to see what we get if we match it with 0.59. Okay, so let's go ahead and check. So we got second vars, normal CDF, negative 1000. We get negative 0.54. And then we times that by 2, and there you go, 0.59. All right, so there you go. So there's two options for how to do that. You can show the Z calculation with the p-value with normal CDF, or you can do the 2-prop Z test, which provides the Z score and the p-value. And usually it's nice to provide a curve so that you can show the two-tailed test. It would be nice to show that. But yeah, so now we can go ahead and conclude. Now for the test, I'm looking for the calculations to show the Z calculation and all that. Although if you did do this part, I will, you'll get credit, but I would rather see the work here. All right, because remember, if you mess up maybe you put the wrong number in here by accident, you're going to get the whole thing wrong on the AP free response if you just relied on the calculator. But at least if you showed the calculations, the numbers, they can give you partial credit for that. All right, so just keep that in mind. All right, so since the p-value of 0.59 is greater than alpha, which is, we forgot to state the alpha, so we need to remember to state that here. So when you do the state here, use alpha equals 0.10. Okay, so we want to make sure that we state that condition, because I think that's what they said, right? 0.10. Yeah. Since that's greater than 0.10, we reject the null hypothesis. There is not convincing evidence that, then now we're going to explain the difference, okay? So there is not convincing evidence that of a true difference, right? Here, in the proportions, right? That there is a true difference, let me say that the true difference in the proportions of all, let me put true difference, freshman minus senior. That might work. All right, the true difference in proportion, and then we included the difference there in freshman and senior use. Senior use of anabolic steroids is not 0. So you could say that the true difference in proportions in freshman and senior use of anabolic steroids, freshman minus senior, is not 0, or you could say that the true proportion in freshman use of anabolic steroids, and we should put in Illinois, is different, that the true proportion is different from that of the seniors, something like that. Okay, so there's a couple ways that you can word it. But that's going to do it for the video, guys. Hope you found this useful and informative, and as usual, I'll see you in the next one.